Hi, everybody, and welcome to Arrangement of Atom Notes. Hope everybody's having a good day. So when we start out here, when we talk about solids, okay, if we talk about solids for a second, we need to think about how solids look. So if we think about each of these as a particle, an atom, a particle, it could be an element, it could be anything small, okay, and we start stacking them up like this. I'm just not randomly putting them like that. We kind of have this idea of how these look. So what could we say about the shape of these? Okay, so we can say it has a defined shape. If you look at something like a block or something like that, it's defined. We could measure it. And if we can measure it, if we have a defined shape, we also can have a defined volume. We literally could measure every side of that and calculate it and everything like that. All right. So we also like to say there is a lot of order here. Now, many of you probably are going, okay, I know what a solid is, but how do these particles move? Okay, well, we have this nice defined shape right there, just like we talked there. See if I can draw my nice cube. Okay, pretty good. But how are those molecules moving? We kind of draw these little lines like this. They're tightly packed in there and they're vibrating. Okay, we like to say that they're vibrating back and forth. Okay. Basically, there's not much space between them. They're just constantly bouncing off each other, almost like John Dalton said. And that's why it's really hard. You can't put your hand through a solid because those little molecules, atoms are vibrating so hard that they don't even allow you to get your space in between. If we were able to stop them, you could slide your hand through, kind of like a ball pit. The next one is a liquid. So if you wanted to, you could pause this for a second and see if you can draw your liquid. All right, maybe you did, maybe you didn't. But if we draw a liquid, instead of like a solid, most of you probably figured there's not as much order. Okay, we kind of have this more of a sloppiness to it, kind of goes like this. All right, so we'll just put over here, there's less order to a liquid. Okay, think about what it has a defined. What could we say? It has a defined something, defined shape or volume. Well, hopefully you said it has a defined volume. Okay, depending on what container we put it in, we can measure that volume, like a graduated cylinder, something like that. We have a defined volume. There's only so much liquid in there. But its shape is going to depend on the container it's in. Okay, if the container is a skinny graduated cylinder, it'll fill that up. You've all seen different types of glasses and everything like that. And even if we had 10 ounces of coffee, depending on what shape the coffee mug is, it will take that shape. So when we look at it kind of more already drawn, we kind of say that the particles are doing this. It's kind of a lot more, let's write that down. It's a little bit more random. Okay, not random, but random. All right, it's doing this. And if you think about it, how would you describe how those particles are moving? They're not vibrating. Imagine you're in that ball pit now and you're kind of trying to swim around. So you could say that those particles are flowing or sliding past each other. Okay, so they're kind of flowing or sliding past each other. That kind of ooey gooiness to them, if that was a word. Gases are a lot different. Okay, gases aren't even at the bottom of a container. They're kind of flying around. We want to put over here. There's a lot of disorder with gas. Okay, if a solid is full order, then a gas is like full disorder. All right, so what does it have a defined? Does it have anything defined? Does it have a defined shape? Does it have a defined shape? No. How about a defined volume? Well, in an open air, we'd say no. If you compressed it in a container, it would take the shape of that container. But truly, it has no defined shape or volume. Okay, it has no defined shape or volume. So, and I think I might have even said the word out loud, but how would we describe how these guys are moving? Well, we'd say that they're flying around and they're bouncing. They're bouncing off each other. All right? They're just all, I would say, and I would say that their motion is very random. They're very random. So again, if we looked right here, again, how would we describe this gas? You can kind of see that it's in this container, but it's bouncing off each other. You can see the contact with the glass. We could say a liquid is, what's our word? Sliding and flowing. And then our solid is vibrating. All right. This is something you actually know. You actually know this definition, the kinetic theory of matter. Okay. First of all, we know this term matter. These are the particles. Why is that not working? The matter, we know that that just means these are our particles. Okay. Theory. All right. Theory is just the idea. So this is our idea, our tested idea, if you will. And kinetic means movement or motion. Okay, so this is our movement idea of particles. All right, so basically it says the higher the temperature of something, of a substance, the faster the particles move. Well, that actually makes a ton of sense. You know, on like water, if you take water and you take liquid water and boil it, you can see the water moving faster. Think about the blood in your body. The more you work out, the more you move around, the more your heart beats, the faster your blood is pumping. This one's a little harder to think about, but at the same temperature, more massive particles move slower than less massive ones. So air, a gas, will move faster at room temperature than a liquid. Obviously, a liquid at room temperature on a counter would slide more than a mass of like a solid object. You could also think about this. If we were in the same temperature, you guys are smaller than me. You are going to move faster than me. And last but not least, we know solid, liquid, and gas a lot, but a lot of us don't know this term plasma. Now, if you just look at this picture right here, what does plasma look like? Does it look more like a solid, liquid, or gas? I hope that you picked it's like a gas. Okay, so pretty much the same idea. We're going to say that it has no defined shape or volume. Okay, kind of takes the size of the container that it's in. Okay, if the container was sealed. But if you notice, we're not talking about just particles here. We're talking about protons and electrons and things like that. These are charged particles. In essence, plasma is not an atom. It's at such a super high temp and pressure that it can only exist at such a high temp and pressure that it's like the atoms have ripped apart to its fundamental things. So where do you think that takes place? Where's something so hot that it could rip things apart? Well, an example of it of plasma are the northern lights or the aurora borealis. These are literally protons and electrons that have shot out in the universe and they scrape our atmosphere. Okay, so where do we see it? I hope some of you thought the sun. Fire, in essence, is plasma. Some of you, I told you, were firebugs. If you look at it, you go, what is fire? Is it a solid? Is it a liquid? It kind of moves like a liquid. Okay, all right. Many of you have maybe gone down to COSI or one of the other parks or museums and put your hand on that static electricity bulb. That's raw electricity. Electricity is plasma. And of course, lightning is plasma. Okay, super high temp and pressures. So again, for our purposes of our class, we need to know these four states of matter. Almost everybody probably knew solid, liquid, gas. But again, if we trapped all the gas, even the gas from boiling water, steam, and held it under high temp and pressures, we can convert all of those steam, water, gas molecules into hot plasma. Okay, and again, this is not the plasma that's in your blood. That's different. This is a state of plasma. And obviously, we have to add an incredible amount of heat to get there. Well, I hope you enjoyed these notes and the arrangement of atoms. So, till next time, Mr. Tima is out.